Hi, good morning, and welcome to the ZP Developer Zone. And we do this every Sunday at 8 a.m. London time. Now, today we've gone ahead slightly early, and really the reason being is we've got so many questions, and I have a hard deadline at 8:30 London time that we really have to sort of jump into it pretty quickly. So my apologies for going early, but if you're joining now and you can see that we're already sort of halfway through, it's just the amount of material or questions that we have this week. So I'll jump into it. Anyway, we have our ZP Academy. It's probably worth saying that one of the answers to one of the questions is in our ZP Academy this week. We do these webinars every week, and we do have collaborations. Collaborations generally happen where there's sort of government funding, and ZP will come in and sort of help. We have jobs, we have our ZP Developer Zone, and we also have our workshops. There'll be questions today about the cortisol sensor, etc. And these are really covered in our workshops. So I will highlight that. As I say, we do have our workshops. There's one next week. So we look forward. There are people obviously coming from around the world to attend that workshop. We have a workshop in Coventry, workshop again in April as well. So our intention is to have at least 2 workshops every month, one in Norway and one in the UK. And there's a link here, so I hope you can attend one of our workshops. Just trying to go quickly. We've had some questions about fabricating carbon screen printed electrodes. I will answer those questions. We've had questions about heavy metal detection. I'll recommend an electrode, and I'll also put links to where we've got data about this kind of application already. We've also got questions about wearable pH sensors, and I will point you in the right directions on both electronics and on the sensor. I've combined a couple of questions here that somebody's interested in making immunosensors around sepsis, things like procalcitonin, which we do have, for example, data on our website about, and also immunosensors or antibody-based sensors for bacteria. So I've combined these 2 questions together. The nice thing about electrochemistry is it's truly a platform, and by changing a recognition molecule, you can change the target, but the fundamental science doesn't necessarily change. We'll also talk about TAS, FRAP, and ORP, oxidation reduction potential. I will focus on oxidation reduction potential today. It's probably worth saying that we do cover that quite extensively in our workshops as well. Advice on gold electrodes, and I realize that question 6 and the last question are sort of overlapping, but so many questions came in, we had to quickly put together slides. We will talk about cortisol sensors. On cortisol sensors, I'll talk about the value of this sensor. Also, question number 8, this one came through YouTube, and it's about the definition of surface overpotential, ohmic overpotential, and mass transfer overpotential. I understand the question is confusion because I just want to say good morning to Hitcham. Lovely to see you this morning, Hitcham. I think there is a lot of confusion over these terms, and I'll try and clean up or give my definitions around this. I'll also just comment on the ecFlex. There's lots of material about the ecFlex on our website. I'll just highlight where that is. Also, I'll touch on the change in performance of a glassy carbon electrodes. Somebody's got some drift in it. It's basically clogging up with polymer. I think the carbon electrode needs to be soaked in the polymer that the electrode is actually cast in, but I will comment upon it. I'll also do I say discussion here, but I'll do some comments on aflatoxin detection, and I'll also talk about analyzing Chillie, and I'll also talk about our sodium sensor, and then ENIG, Electroless nickel immersion gold, ENIG, Electroless nickel immersion gold as a surface in biosensing. So 14 questions. Like I say, we had to start early, and simply so much material to get through. It was going to take more than half an hour, so I had to go in quite early this morning. First of all, somebody's interested in fabricating a screen printed carbon electrode on SPCE. They're asking what's our print thickness, whether we use PET or PVC or ceramic, and what target range should I target? What thickness range should I target? So the quick answer is we do produce a lot of high value, hyper value carbon electrodes. They are done on PET, and I think the print thickness is about 12 to 15 microns. And I will comment on that a bit. First of all, it's probably worth saying that we actually have a course on the ZP Academy for Introduction to Screen Printed Electrodes, so maybe check out that course. Then on print thickness, I've got a. If you see a link, I will have already put the link underneath the video. So hopefully I did remember to put that link underneath the video. But we do have a. We've literally dragged a profilometer across many of our electrodes, and we've actually measured the sort of step height due to the print thickness. So that's why I'm getting this 12 to 15 micrometer print thickness. It's probably worth saying that people, I think, the academic value in producing carbon screen printed electrodes or screen printed carbon electrodes is probably very low. The reason I say that is because printing screen printed carbon electrodes, I mean, this started in about 1984, so that feels like about 38 years ago. So the value really, to society and the improvement and advancement, which is what academia is about, is actually very limited because it's been done for such a long time, but that said, I think that the problems in carbon electrodes is not the materials, it's actually the repeatability of manufacturing. So at ZP, we are, ISO 13485, and I know HITCHAM's online, but, something that we're really pushing on these days is if people are, doing lab work, and that lab work could also be the manufacturing of, carbon electrodes, you really need to be doing high throughput testing, or high numbers of testing, I should say, to make sure that, well, really to work on repeatability. You can always make something that looks visually, let's say, repeatable and quite nice, but actually then you sort of do a electrochemical functional testing on it, and you find out that actually it's quite variable. So I do try to suggest that people get sort of parallel potentiostats. We have a parallel potentiostat, and that's what we use to do a lot of quality checking. So, we'll produce a batch of electrodes. We may test more than 6, more than 12, but this instrument allows us to do 6 or 12 at a time in true parallel. So we kind of get the CVs, make sure, we just use CV, with ferricyanide just to kind of indicate that, it tells you a lot, does a cyclovoltammogram. It tells you the sort of surface area, whether there's a resistance problem in your conducting tracks. So we do like to use CV quite a lot. And we actually then use Djuli as well to analyze our data. So as I say, the problem so much in making carbon electrodes in particular is not making the carbon electrode. I mean, you can use PET, you can get a print thickness of 12 to 15 micrometers. It's actually the repeatability. A lot of electrodes that are sold on the R&D market are not repeatable. It really gives, the technology is sort of a bad reputation. But we actually have Djuli, which can then sort of automate things like our peak height and our peak position analysis, and it really helps us check for repeatability. So I'll put a little link up to Djuli here. Hopefully you can set up a free account on Djuli, and it allows us then to kind of go in there and actually understand what our repeatability is. So we do get a coefficient of variation, or our relative standard deviation of, we always aim for 5%. This batch is, for example, 4%. So we're pretty good on the repeatability. And Djuli is really good because we can set criteria then and say, look at those peak. In this case, those peak separations. We set a rule, and we can then, Djuli will just check whether the data for each one of these tests is actually passing that rule. So we can pass those. And then we might set a rule on peak height, and Djuli would check to see if those are the peak heights are within a criteria as well. So that you can see there that by knowing, the peak separation, the peak height, we can start, saying, are these electrodes in our test performing within criteria, and we will pass or fail them. I think it makes it so a little bit unique that at ZP, it's not so much about the fabrication of the electrodes, it's actually making sure that these electrodes are good. And I think we're the only ones that do this mass testing, let's say, at scale. And you can spot things, gross errors. We wouldn't never ship that, we would never ship that, for example. And Djuli will, help us do that. We do something called wafer mapping, which is actually essentially having a coordinate. If we print a sheet, we can sort of test the entire sheet and then spot a bad, electrode and reject it. And so, it does allow us to ensure that we're not shipping things. And we also do what we call a run sort of map, to make sure that every sheet, not every sheet, but we test beginning, middle, and end to make sure that everything is within specification. The thing about repeatability is we're ISO 13485, so we're certified for doing quality development, quality manufacturing, and really need that in order to get the repeatability. Now, question number 2 is really about how to do heavy metal detection, cadmium, mercury, lead, magnesium, etc. And we do have some notes on this. I have some data up on the website about lead and I think also copper. I am going to put some links in a minute to that. It's the same thing as well, that we will support people in this kind of work, but we will only support them really on our own screen printed electrodes and our own potentiostats. So I'll make a recommendation and I'll link to the potentiostats that we support, and I'll put a link to the electrode that I'm going to advise. So the electrode I'm going to advise is the hypervalue carbon electrode. The data I show on our website, that's with copper and lead, and we know it works. And so, yeah, I've put a link here to the potentiostat that we support, and I'll also put a link here to the carbon electrode that we support. It's probably worth saying that these carbon electrodes, if we sell a sheet of them, it's 250 euros, but it's less than €1 per electrode. And I understand that depending on the region, this can be expensive, but on a global perspective, it's actually quite low cost. But it's also the quality that's important as well. So we recommend the hypervalue carbon electrode, and we recommend it with our EMA potentiostat. As I said, we actually do have some data. They've got a whole stream of images or data up on our website, and I've put a little link to that. Question number 3, somebody wants to make a pH sensor for measuring pH in a sort of wearable application. They also want to have temperature sensing in there as well, and I'll make a comment on temperature sensing as well. This ties in a little bit with an EasyFlex question that's later on. So EasyFlex is a product that we produced somewhere between 5 and 8 years ago now, and ecFlex is something that we're sort of blending out, let's say, and we're replacing it with some new electronics. So the new electronics are really a derivative of things that have come out of our fish tag program. So I will put a link to this. So we are making both wearable and implantable sensors, and we're making them for very challenging environments. And one of those challenging environments, for example, is putting sensors. This fish, by the way, is not dead. It's anesthetized. So the sensor actually is in the fish, and the fish goes on to go back into the fish. I want to say pond, but this is for the production of fish, salmon in Norway. So I've got a little link there. So that sensor is something that we've been working on. What I want to focus on is actually the electronics of that. So that's my finger, but it's the same finger in the shot there. So you can get a sense of the scale of the electronics. So that electronics will run a pH sensor. I will talk about, it also has temperature sensing on board as well. But I just want to say, for R&D purposes and low volume manufacturing, we have a price on our website. We also have a link here. But we've also now produced what we call a test board for this electronics as well. Oh yeah, that's right. So the temperature sensing that you want is 0.1 plus or minus 0.1 degrees C. What that board actually has is plus or minus 2 degrees C, which I know is not super, and nowhere near the accuracy that you want. But that's what we have off the shelf. Now, if we were going to do a custom development with companies like ZP is really quite an expensive effort. Custom work for ZP, a small project could be like between 50,000 and 250,000 euros. But what's nice about ZP is that we put a lot of tech on the website so that people can actually essentially not use our labor, use their own labor, and start making themselves or start saving themselves some money. So here's the electronics that I recommend for your pH sensing, but just know that the temperature is not what you need it to be. We do now have a test board, which a test board is really a sort of carrier. So I've just sort of shown a few shots here, and I'll also show a URL. The electronics I showed earlier on, you really need this with the test board. If you're an electronics engineer, you can maybe get away with just using the single purpose electronics, but I would recommend that actually you get the test board, and I'm more likely to support people who have the test board, because then the electronics fit onto the test board. You can make good connection. We've got connectors here for things like the pH sensors. We've also got connections that allow people to put essentially what we call banana plugs in here as well. So hopefully I do have a link. Yeah, I do have a link for the test board. So it's really the test board that I would I would actually guide people towards adopting that, because they're less likely to sort of fry the unless you're a really good electronics engineer, then you can just get away with using the single purpose biosensor circuit, but otherwise get it with the test board as well, and the link is here. Now, in terms of pH sensing, whoops-a-daisy, we've got a couple of pH sensors. One of them is made out of ceramic, the other one's made out of PET. I can't advise you which one is best. I think, unfortunately, you have to try them and see which one works best in your application. I understand your application, it's a bodily fluid. The pH is probably more acidic than anything. So I think both systems will work. In the long run, if you were trying to make a product from this, I would be recommending you towards the PET sensor. Now, the next question, I've sort of mixed up a couple of questions here. So we had a very nice email from a very nice gentleman in Scotland. He was very interested in making biosensors for sepsis. And I was sort of say basically making immunosensor, and somebody else then was actually, in some ways, it's actually quite related, but they were trying to detect bacteria and they were doing it by antibodies. So I just put a link, and I probably haven't put this link underneath the YouTube video. This is a paper. I've brought this paper up lots and lots of times in the past. It's just such a simple paper. You can take our screen printed electrodes. I also recommend the hypervalue carbon electrodes. Why? Because we make it in such high volume. Why? Because we use it so much. Why? Because we do so much testing. So it does have a good repeatability and a good quality, and people can then build their science upon it and hopefully ultimately their product. In that paper, we describe the activation of that surface using pyrene NHS. With that, then you can just actually sort of attach your antibodies fairly effortlessly to the surface, and then you can actually block the surface then for what's called non-specific binding. As I say, check the details hopefully in that paper. We use cyclovoltammetry when we do this kind of work to understand that we are actually changing the electrode as we go. So the cyclovoltammogram becomes more distorted as we add on these extra layers onto the electrode. In the testing, the kind of methods that I prefer are EIS, electrochemical impedance spectroscopy, square wave voltammetry, and differential pulse voltammetry. In this paper, we ended up building what I would call a sort of a blocking assay. We had all the antibodies, and then either let's say the protein if you're working on sepsis, or the bacteria if you're working on a bacteria sensor, sort of blocks, and the signal changes accordingly. As I say, we'll support this if people are using our electrodes, and if they're using our potentiostats, then we're more happy to support them through this webinar format. And then you can sort of measure signal versus concentration. It's probably just worth saying that this is not the most amazing results ever. So here we show a sort of some signal versus concentration effort from us. And it's not bad. There's actually 3 data points here, 3 data points here. So you can see that our reproducibility is better when we're at a higher concentration. 3 data points here. There's probably 2 there and 1 there, 2 there, 1 there. So you can see that at lower concentration, we do lose a bit of our sort of reproducibility. But I just want to say, that this stuff's not, it's not shorts. It takes us who do this every day, day in, day out, something like 111 hours to do work like this. I realize now it's 8 a.m. or coming up to 8 a.m. I need to go a bit faster. So somebody was interested in making, I think they really want to make their own TAS sensor, total antioxidative status, or FRAP, ferric reducing, ferric reducing plasma. I forget the term for FRAP, but ORP. These are really ways of measuring antioxidants. I'm only going to focus on the ORP this morning because we've got a lot of investment ourselves in TAS and FRAP. You can buy the TAS and FRAP sensors, at least the TAS sensor, off our website. The ORP, oxidation reduction potential, is a form of potentiometric sensing. We do a lot of ISEs, ion selective electrodes. These all fall under this potentiometric umbrella. It's probably worth saying that in our workshops, and I hope people will come to our workshops, we do a lot of deep dive into ORP and ion selective electrodes. With these ORPs, obviously we're not making this kind of form factor when we do an ORP. We're doing more of a thick film printing technology. I will recommend one of our platinum electrodes for ORP in a minute. But when we're doing that kind of work, essentially we're replacing the idea of a platinum and a reference electrode with a platinum and a reference electrode. I know some of our platinum electrodes look very black, not shiny. It's really just a roughness, but they work perfectly fine. So with an ORP sensor, essentially the platinum is able to give up ions or take on ions, and the voltage changes accordingly. So this ability of the solution to take away or give ions is a kind of reflection of its ability to oxidize or reduce. And so it's actually the governing equation behind this is something called the Nernst equation, which kind of says that the potential is proportional to the log of the analyte. Now it's a bit different with a ORP sensor because you can have lots of analytes contributing towards this, whereas an ion selective electrode, is specific to sodium or potassium or ammonium. But anyway, it took me a long time to make a recommendation, so I would recommend, whoops-a-daisy, our platinum electrode, and I've put a link underneath, hopefully also underneath the video on YouTube. I will go, and also, like I say, we are much more likely to support people on their work if they are using the potentiostats from ZP, and these are really quite good. I mean, this is a 6-channel potentiostat. It's absolutely tiny, as you can see, which is is a really nice elegance. And the fact is, you can run 6 experiments at the same time. And to be frank, it just makes for better science. That otherwise people are making conclusions based on like one experiment, and it just doesn't cut it. I think the world of biology is where we have to learn from. At ZP, we want to get to where everything is standardly run at 96 experiments at a time. That's what biology does, and they do it because their signal in biology is often quite weak, so they need the statistically significant numbers. Well, for us in chemistry, electrochemistry, biosensing, our signals are sometimes stronger. But by doing, at least 6 at a time, and ultimately we like to get to 96, you just get so much data that you can be very sure on your conclusions. So anyway, I have linked to this potentiostat, and I would hope that people are essentially using that. We did get a question. Somebody had a problem. They had a problem of reproducible gold electrodes in their lab. They wanted us to make a recommendation. We do have a really, really good gold electrodes. We've been using it in our own work. This is it used as an immunosensor in EIS. There's 3 gold electrodes here, 3 gold electrodes here, 3 gold electrodes here, 3 gold electrodes here. So we get, even though we've functionalized all that gold, with at least antibodies, coupling agents, blocking agents, the signal's still very, I want to say, reproducible for each concentration. And that's really a reflection of the underneath gold. So I've put a link to that data, and I've also put a link to where you can find the gold electrodes as well. So I can't recommend them high enough. Something that I've forgotten to do, though, is we do have some videos on our website cleaning gold electrodes. We have a solution for cleaning gold electrodes. I should emphasize that now, that I think people get screen printed electrodes. I'm sure not everyone's doing this, but sometimes they don't realize that gold tarnishes quite quickly. So whenever we use gold, either we're about to manufacture upon it or we're about to just use bare gold. Most of the time it's manufacturing upon it. we do clean it. We do have a cleaning solution, so be careful because gold tarnishes more rapidly than people realize. Now, I'm always very disappointed on the cortisol sensor. We've had 2 inquiries about the cortisol sensor. We do have a cortisol sensor. We have tested it in the clinical range. Pretty impressed with its performance. But we do ask if people are really serious about engaging us on the cortisol sensor, that they come to our workshops or they actually start a program with us. The cortisol sensor is one of the most sought after sensors in the world. We are working with very well-funded startups and very large companies around the cortisol sensor, and we just don't have the bandwidth to be able to support lots of sort of R&D programs. So we do limit the availability of the cortisol sensor, and if people really want to engage with us, unfortunately, it does have to be through a program on the cortisol sensor. So I'm sorry to deliver disappointment, but I do want to address and recognize that people are asking these questions, and we're not the kind of company to ignore those questions. Now, question number 8. Somebody's confused. This one came through the YouTube channel. I mean, I just want to say good morning to Aftab. Aftab, my apologies. We've come on. I had to start half an hour early this morning. Just so much material to get through. But your timing is quite good, Aftab, because I'm going to deal with glassy carbon electrodes in a minute. But anyway, this question came through the YouTube channel. Somebody is confused by the term surface overpotential, ohmic overpotential, and they're also confused by this mass transfer overpotential. I agree. It's a mess. People are using these terms, and there's lots of terms that mean the same thing. So I don't like the way because of my background, I don't often show potential essentially on the y-axis and current density on the x-axis. I tend to actually flip them 90 degrees. But I think the terms that I'm being asked about today really come from the battery and the fuel cell industry. But if you want to do an oxidation or reduction, for example, you might apply a potential, and you will at some point get a sort of turn up in that potential. Now, I would call this the kinetic region, but I realize that people are calling this the sort of surface overpotential or the activation overpotential region. So I'm going to answer this question on a couple of slides today. But if I was looking at this perspective where it's potential on the y-axis and current on the x-axis, then you're essentially increasing the potential, and then the current here is increasing, and that's really their then term in that the surface over potential. Now at this point, this is a sort of plateauing, or it's changing a little bit. Now they call this the ohmic over potential. I would call this the mixed control region. That's why I say it's so confusing, because actually people are using different terms depending on really the application. Like if when I reverse this, or when I change the axis, you'll see that this looks like linear sweep voltammetry. But if you're in the battery or fuel cell industry, then you tend to look at it this way, and you use these terms. Whereas if you're in my side, I'm not calling that ohmic potential, I'm calling that mixed control region. And then you have this region where actually the current no longer increases, and you've hit what's called the mass transfer over potential. I would call that the sort of mass transport limited region. So you've got over potential on the y-axis, current density on the x-axis. In this region, I would have called it the kinetic region because I'm under electron transfer control. But some people are referring to this as the surface over potential or the activation over potential. I would then refer to a region between this area and this area. I would have called that the mixed control because it's a mix between mass transport and kinetic control. At this end, it's more kinetic control, and at this end, it's more mass transfer control. But ohmic over potential is just this term that has these two phenomena sort of mixed up into it. Now, like I say, I prefer to actually, I don't like, well, it's just the way I'm trained, I'm educated. I flip the axes slightly, and I have over potential this way and current density this way. And so then I have this kind of region where the there's not enough potential in order to cause a electron transfer. Then I hit this region, which some people are referring to as the surface overpotential or the activation energy. Then I hit this kind of region, which I would call mixed control, but some people are calling it ohmic overpotential. And then we get this flattening off, which I would call sort of mass transport limited current. But I can see that some people are calling it mass transfer overpotential. There's lots of terms for it, and that's the confusion of it. So I think it's really a confusion on definitions. I don't think this person has a confusion on understanding. It's just when people are using so many definitions, it is, in the end, confusing, and they're all sort of you can change one for another. I just want to say, I know a bunch of people have jumped on this morning, and we actually started the webinar 40 minutes ago, and it's just really because there's so many questions this morning. So my apologies if we're a little bit confused. Don't worry, everything's recorded. You can go back to the start and essentially catch up with us. Question number 9. I am conducting a feasibility study. They want to use the ecFlex. They say, do we have a reference manual data sheet? The quick answer is there is a data sheet and there is a quick start guide. So I think you've got the two things that you want. I mean, we got a lot of information. I think you found the page. You just don't realize that the page is so long because this is one of our oldest products. I've previously, now in this webinar, mentioned the single purpose circuit, and I've also mentioned the single purpose biosensor circuit with test board. These are the products that I think you should really be focusing upon these days. And the ecFlex is something that we're blending out. But for completion, I have put the link here because you asked for it, and we do actually have the information, and here's the link. So this one is somebody has a change in performance in their glassy carbon electrode. What I first want to say is you'll see a couple of a really nice set of slides now. Please understand that the set of slides I'm about to show actually mainly came from the questionnaire. And that's really great because they've bought a product from ZP, they have some questions, they've prepared a really nice slide deck. And, you know, that's to be respected because obviously they're trying to make our life as easy as possible. So they've had a change in performance in their glassy carbon electrodes. You know, so we do sell a glassy carbon electrode. It has a 3mm diameter working electrode. It's a personal opinion, and I know it's a bit strange of me, but I'm not a super fan on glassy carbon electrodes. I did do my PhD on a glassy carbon electrode. So having used one, then to say I'm not a super fan of them. The reason I'm not a super fan of them is because I'm really interested in biosensor development and commercialization, making real products. And the glassy carbon electrode doesn't lend itself. It's an okay R&D tool, but it's so different from something that I could consider as low cost, something that I could give, you know, to other people and they could use it in the field, like our Chillie sensor, for example. It's just, it's a very R&D tool, and I feel like it locks people into an R&D mindset, whereas I want everyone to have an entrepreneurial mindset. Anyway, glassy carbon electrode is something that we make, and they obviously they understand how to clean it and how to test it. So these people clearly, you know, have done their homework and they exactly know what they're doing. And they just have a question, which is, they then, as I say, these are their slides, you know, so they're extremely professional in the way they've presented it. So they show us the glassy carbon electrode when they first get it. I'm just checking now. And after, which is kind of interesting, after 30 to 40 uses in about 1.5 years, you know, it's changed. Now, the changes are obvious to you, but essentially the peaks have got smaller, and the peaks have essentially gone to either more positive potentials on the oxidation wave or more negative potentials on the reduction wave, but the peaks have essentially come away from one another. So that for me is really indicative of an increase in resistance. So obviously, you know, their theory is that, you know, the resistance is due to the, well, they're asking what my opinion is. My opinion is it's resistance, it's increasing resistance. Now you know, you would immediately blame the glassy carbon electrode, but I did get them to do some other stuff for me just to make sure that it probably was the glassy carbon electrode. They also sent some other data here as well. They're doing differential pulse voltammetry. as I say, I'm a big fan of differential pulse voltammetry and square wave voltammetry and EIS. These are good methods when doing, especially doing analytical work. Which is interesting actually, because Hitcham's online and he just recently did his PhD. Got his PhD in essentially electroanalytical chemistry. So they did some first measurements. They had a nice big, essentially wave here, but it's decreased over time, and it's also gone to more positive potentials. It's the same as the cycle voltammetry, that essentially there's an increase in resistance that's going on here. And you can see it very clearly in the EIS. This is what's called a Nyquist plot. If some of this is new to you, I'm pretty sure many of you actually, it's not so new, but we do cover all this kind of stuff in our workshops. You can literally see it, that there's this in the Nyquist plot, there's a sort of semicircle here, and the diameter of that represents the charge transfer resistance. And that charge transfer resistance has been increasing over the years. I got them to send me a picture of the setup. It's just trying to look for things like obvious things like corrosion on the connectors, but I mean, these guys, it's all set up pretty well, so I can't, say that was the issue. What was nice though is that they did give me images of the glassy carbon electrode, and then they told me about this drop casting, and then that was the kind of hint to me, because I was a bit confused. I mean, like I say, I've used the same glassy carbon electrode for like 3 years during my PhD, and that I did inherit it, so I know that they're pretty robust, but they're drop casting. So that's my theory at the moment is this is a sort of idea. This is a side-on view of the glassy carbon electrode. Here's the sort of carbon disc at the end of that, and they're drop casting, and then they're essentially curing onto it. So their theory is that actually they're able to remove that by just polishing it. But I think that glassy carbon electrodes, they're more porous than actually people realize. And I realize that, if their polymer is essentially getting into some of the sort of structure of the carbon, they may not be able to polish it back out again. And that would essentially be blocking the surface. So I think the surface is being irreversibly modified because the polymer is getting into the surface. I'd call that a little bit of absorption. And I know they're polishing it, but I think also glassy carbon is actually quite hard. So if it's a softer material, you could literally polish the surface off. But I think that actually the polymer's got deeper. And of course, the polymer is an insulator. An insulator is a resistor. So I say that they've got a problem of increasing resistance, and so the theory sort of fits the observation. I don't want to start suggesting SEM imaging, but they could do SEM imaging to see this. How to fix it is a question. Well, to be honest with you, I think the answer to how to fix it would be, I don't know what solvent they are casting in, but clearly their polymer was initially soluble in that solvent, so sort of soaking it in that solvent. But even then, I suspicion that it's going to be very hard to get it out. So I don't think it's the carbon itself. I think there's residues of polymer getting into that surface, and they're not getting it back out again. I'll just make some more comments and then we'll move on to the next question. So in summary, they've got one of these glassy disc electrodes. Well, what I find interesting is that they were doing 30, 40, 50 experiments on that, 30 to 40 times from their notes, which is interesting to see, because actually I'm much more of a fan of hypervalue carbon electrodes. I think it's much more representative of a real product. And then I realized that they've unfortunately got 30 to 40 tests out of that glassy carbon electrode, whereas the hypervalue carbon electrodes, a sheet like that would be like 250 euros. So 230 euros, 250 euros, but there you get 300 electrodes, and it's 300 pristine electrodes each time. So I do think that is a better, and I obviously, because I like the fact that I want people's science to become products, and glassy carbon electrodes are nice for R&D, but they don't lend themselves towards necessarily becoming products. So I would make a recommendation that they actually use screen printed electrodes. But now aflatoxins, we had this image come in. Somebody was asking about In general, they're interested in detecting aflatoxins. I would say that using our screen printed carbon electrodes is a good idea. Aflatoxins are kind of interesting actually because they're very electrochemically active. I've got colleagues at the moment trying to use aptamers for aflatoxin detection. Problem with aptamers is it adds a complexity to the sensor, adds a cost to the sensor. I'm not convinced by aptamers. They happen to be using gold as well, so they kind of got a gold electrode with a thiol linker to aptamers. So I'm not a great fan of the idea. At ZP, we actually have what we call the spectrum sensor. I'll put a link here, and the spectrum sensor works in conjunction with our SenseIt platform. So to be honest with you, how hard is it to detect aflatoxins? It's not hard at all, actually. It's quite straightforward, especially if you're using this platform. The problem that people have is they sort of overcomplicate the sensing, really, by trying to use sort of recognition molecules, when our approach to this kind of work is, I'm biased, but is a lot more elegant. I mean, keep it simple, is my kind of motto in life. So I do have put a few links to a sensor, and I've also put a few links to a hardware technology. It's probably worth saying at ZP we have what's called an API policy. So if we can work with people with our sensors and our electronics, and we can get the data to the cloud, then they can use the data in their own applications using what's called an API call, Application Program Interface. Just something else that came in this week was really interesting to me. In some ways, our food sense technology for measuring the hotness of chili is a sort of a derivative of our SenseIt platform. But these kind of products come in, and people ask us to measure the hotness of them. The active molecule in this kind of material is actually capsaicin, and we're able to sort of look at their product, and we're literally able to see from the peak heights how much capsaicin is actually in these products. And so when we tell people what their Scoville heat unit is, it's not this sort of guess. It's not even HPLC, and with HPLC, there's a large large sample workup that they have to do, and then they have to get what's called a chromatogram, and then they have to compare the chromatogram against the calibration slope. Our food sense literally gets the fingerprint for capsaicin, analyzes the peaks, and then analyzes the area under the peaks and says that's how much capsaicin is in there. It works really quite elegantly. It just occurred to me that actually the same principles could be transferred over to aflatoxins as well. We did have a question that came in on sodium sensors this week as well. Things like, what concentration can we measure? How long does it take this solution to dry? And then also about the barrier layer to dry as well. I just realized that we do have a video on adding barrier layer. I apologize, I haven't put it in here, but there is, if you can Google around, there is a video on ZP barrier layer where one of our guys adds it, and the drying time should be about 15 minutes. So in terms of our sodium sensor, I mean, it's designed to be using the clinical range. So that's 40. Well, the clinical range is about 135 millimolar. So we test it at 40, 80, 160, 320. These are really classic kind of steps. So, we're pretty confident of it working within most, at least human applications. And we do have an activation solution. So if people don't want to buy our sensors, you could buy our hypervalue carbon electrodes, for example, which I've referenced X number of times today. And you can essentially make your own sodium sensor. I have a video activation of an electrode for ammonium out there. It's the same procedure. So watch that video, and you should be essentially good to go. Last question. I'm sorry to I had to start early today, but even by starting early, it's 8:23, so I was right to start, let's say, super early. So what I want to do now is talk about an inquiry that came in called on Electroless nickel immersion gold. Be really careful about using Electroless nickel immersion gold. I know the inquirer's already seen this video, but PCB manufacturers, people try to sort of just thicken the gold up and overcome what's called an underlying corrosion issue with this kind of technology for biosensing, it never works. I've known companies that have been trying this for years of just thickening the gold, and it just doesn't work. The gold is just too spongy. Or for a while it works, and then suddenly it stops working, and everyone's sort of scratching their heads why it stopped working. I would obviously recommend one of our gold electrodes. It was question number 6 today. I'd already sort of hammered on about how good our gold electrode was. I've said this before. Hitcham and Aftab have both heard me tell this a lot. Biggest use of these gold electrodes is ZP. Therefore, the quality has to be good, because the first people to be impacted by this would be us, and that's a really big difference between us and other manufacturers. So why do I recommend our gold electrodes? Because, as I say, we use it, we know it works in these kind of biosensor applications. Fundamentally, it's a very reproducible, and it also has the robustness necessary for these types of applications. We do have other types of gold as well. We do have a sputtered gold. We have used sputtered gold in the past. Somebody wanted a very pure gold surface, so we did make a sputtered electrode, and we also have a sister company called Massius that does actually produce a gold electrode on a PCB, but they have a very proprietary technology that means that they can actually get away with this, or they can do this, whereas other people just struggle. I've put the links here. So my recommendation is, if you think that ZP has a solution for you, buy some of the hypervalue electrodes, buy some of the sputtered, buy some of the Massius electrodes, and try them out and see which one works. Because then you know that the materials work. Otherwise, you're going to spend months negotiating with vendors and then find out that the material doesn't work. So you've wasted something of the most valuable asset that you have is time. Buy the material, check that it works. If it works, then you can engage with that inquirer. So fabrication of carbon screen printed electrodes. Sure, the hyper value is made on PET. It's about 12 to 15 micron print thickness. Heavy metal detection. I have linked to data for copper and lead. Use the hyper value carbon electrodes as an example, but please use the EMA potentiostat in order to get as many channels of data as possible. Wearable pH sensor. I've definitely linked you to the right electronics for that, and I've also suggested 2 pH sensors. I would say that you need to use the test board with the single-purpose biosensor circuit on it. What I haven't been able to say to you is that we've got the temperature plus or minus 0.1 degrees C. We could do it as a project, but I think you can also find other solutions out there when it comes to temperature. Immunosensors for sepsis and bacteria. There's a nice paper there. I would suggest you have a quick look at it. On the ORP, I would suggest our platinum hypervalue electrode and obviously the EMA potentiostat. On the gold electrodes, I've definitely linked to the gold electrodes, and I've also demonstrated to you our reproducibility and also the fact that we do the biggest users of these electrodes. Cortisol is never a happy answer to that one, which is we do have the cortisol sensor, and it's used really on big programs. It's such a valuable sensor to us. We have to be really selective and careful in who we actually work with on that cortisol sensor. This was a fun one, question number 8, hard question, because actually these different definitions, it's just there's no consistency between the different applications in electrochemistry, but I hope my video, a couple of slides, has helped you a little bit there. ecFlex, don't worry, there is a manual and a data sheet, and we do have them in stock. As I say, we are actually going over to the single-purpose biosensor circuit, but ecFlex is there. The changes in performance of the glassy carbon electrode, I think to really fix this, you're going to have to go into the you're going to have to soak it in the solvent that you were originally sort of drop casting in. But really, you might have to leave it there for several weeks. My main recommendation is, if you're trying to make, they may be making a catalytic material for fuel cells or batteries or hydrolysis or electrolysis. So there, I can understand they don't want to use screen printed carbon electrodes. But if it is biosensing, just use screen printed carbon electrodes. Otherwise, you're going to have to do a long soak in the organic solvent. But I can't recommend that it is necessarily going to work. Discussion on aflatoxins. So aflatoxins, I do agree. I'd actually be using our Sense It All platform and sort of essentially commissioning us to be engineers on the project to provide the sensor and the electronics, and then you can get the data through an API application program interface. And analyzing chilies just showed you that actually, we can see the capsaicin directly in the chilies, which is probably similar to doing the aflatoxin work. Sodium sensor, clinical rate, well, we've tested at 40, 80, 160, 320 millimolar. I have a video on casting an ammonium sensor down. Watch that. And I also have a video on the barrier layer as well. Those videos really should be enough to get you essentially going. Electroless, nickel, immersion, gold. Be really careful with it. The only company I can recommend on that is Macias. Obviously, it's a sister company to ZP, so you've got to understand that. Get some gold electrodes off us, both the screen printed, the sputtered, and the Macias sensors. Find out which one works the best, and essentially take it from there. And I then want to just say thank you, and I want to say a special thank you to Aftab this morning. I really appreciate the smiley face, Aftab. I've literally been given this for now 1 hour, so know one thing: even if we weren't able to give a completely satisfactory answer this morning, at ZP, we will try and at least attempt to recognize and then answer all the questions that essentially come through. So much thanks to Aftab this morning. I hope that will help our mutual friend with his glassy carbon electrodes. And thank you to Hitcham this morning. Congratulations on receiving your PhD of recent. And I'm sorry I wasn't able to attend the Viva, but I'm very proud of you. Okay, take care, guys, and speak to you soon.